Hi, I'm Kuan-Chuan Peng from Mitsubishi Electric Research Laboratories, MERL. I'm going to present my work entitled Iterative Self-Knowledge Distillation from Pothole Classification to Fine-Grained and COVID Recognition. Detecting potholes is essential for the road authorities to repair defective roads. The vehicle repair bills related to pothole damage have cost U.S. drivers $3 billion annually on average. Due to the cost constraint of the edge devices which the pothole classifiers run on, the edge devices installed on the road inspection vehicles may only have limited computational power, for example, no GPU. In such scenarios, lightweight models are needed if real-time inference speed is required. Motivated by this application and deployment time constraint of pothole classifiers, we focus on the following problem. Given a fixed number of training epochs and a lightweight model to be trained, what can practitioners do to improve the pothole classification accuracy? Given the problem, we explore self-knowledge distillation, KD, to tackle pothole classification. By self-KD, we refer to the KD methods which need no teacher model in advance and introduce no extra trainable parameters. Showing that KD is actually learned label smoothing regularization, Yuan et al. Proposed a teacher-free KD method by using the pre-trained student model itself as the teacher model. Inspired by Yuan et al., and the assumption that better teacher models result in better student models, we propose iterative self-knowledge distillation, ISKD, which iteratively performs self-KD by using the pre-trained student model as the teacher model. We make the following contributions. First, to the best of our knowledge, we are the first in pothole classification to use iterative self-knowledge distillation when training lightweight neural networks under limited training epochs. Second, we propose iterative self-knowledge distillation, ISKD, which outperforms the state-of-the-art self-KD method on 3 pothole classification datasets, 2 generic object classification datasets, 3 fine-grained object classification datasets, and the COVID-19 radiography dataset, which supports the wide applicability of ISKD from pothole classification to generic, fine-grained, and medical imaging classification. Third, we provide more evidence showing that even using a teacher model with accuracy lower than the baseline accuracy from a classifier trained with a larger number of epochs, the student model can still possibly outperform the baseline. Fourth, ISKD can outperform the baseline under a wide range of weight, balancing the objectives of ISKD, which supports that ISKD is flexible with respect to parameter selection. We illustrate ISKD here, where we denote the teacher and student model in the KD iteration, IK, as TK and SK respectively. During I1, since T1 is not given in advance, we train S1 using the softmax cross-entropy loss, LC, as the classification loss. During IK, when k is larger than 1, we use the train sk-1 as tk and train sk with both LC and the KL divergence loss. Specifically, the total loss function LKD to train sk during IK is shown at the bottom, where KLD is the KL divergence. ZT and Z are the output probability distribution of TK and SK respectively, and alpha is the weight of KLD. During IK, we freeze the parameters of TK and only train SK. We pre-train SK from ImageNet, not from SK-1, because we hope to decrease the chance that SK is trapped from the possibly local optimum associated with SK-1. ISKD stops at IK if SK shows no obvious accuracy gain over SK-1. We expect that using ISKD improves both TK and SK when K increases, under the assumption that using better teacher models in KD generally results in better student models. We experiment on 3 pothole classification benchmarks, RDD, near-neighbor simplex, and complex datasets. The red bounding boxes in the example images are the pothole annotations. We also experiment on 2 generic object classification datasets, CIFAR 10 and CIFAR 100, 3 fine-grained classification datasets, Oxford 102 Flower, Oxford 37 PET, and Caltech UCSD BIRDS 200, and COVID-19 radiography dataset. We summarize the statistics of all the datasets in the table below. The experimental results are summarized in Table 1, where we refer to each column by the experiment ID E1 to E9. All the numbers are reported in the format of accuracy subscript, the number of epochs which the student model is trained for. E1 to E6 lists the performance of S1 to X6, and E7 summarizes the last performance after I1 to I6. There is no teacher model for E1 and the large epoch baseline E8, but for the baseline using TFKD self E9, the teacher model is the trained S1. All the student models are pre-trained from ImageNet for ISKD E7 and the two baselines, E8 and E9. In Table 1, the accuracy of E2 is higher than that of E1, which shows that self-KD can improve the student model's accuracy. Table 1 also validates the assumption that in self-KD, better teacher models result in better student models, and that self-KD can be done iteratively instead of just once. Comparing E7 with E8 and E9, we show that given a fixed number of training epochs, ISKD outperforms the large epoch baseline and the state-of-the-art self-KD method, TFKD self, in most cases. The fact that E7 outperforms E9 is also an ablation study supporting that self-KD is better done iteratively than just once. Since Table 1 covers diverse task domains, including pothole, generic, fine-grained, and medical imaging classification, our results support that ISKD can serve as a general-purpose performance booster. In addition, we obtain the results in Table 1 by directly using the alpha values chosen for pothole classification without tuning the alpha values for each dataset, which supports that alpha values we use are transferable across different datasets. We also compare the accuracy of ISKD using ResNet 18 as the backbone with the prior methods, which use the backbones with more parameters in Table 2, where ISKD performs on par or even outperforms the listed methods, which use more parameters. This finding supports that ISKD is more parameter efficient than the listed methods. Furthermore, we analyze what is the worst performing teacher model in self-KD, which can still make the student model outperform the baseline with no KD, which is E1 in Table 1. To gain more insight, we designed the following experiment to find the accuracy relation between the teacher and student models. Given that E1 in Table 1 is trained for 50 epochs, we use the 50 models saved after each epoch is completed as the teacher models. We repeat E2 in Table 1 for 50 times, each time with one of the 50 teacher models produced during E1, and record the teacher-student accuracy relation in this slide. Most of the data points are above the red line, x equals to y, which supports that performing self-KD can make the student model outperform the teacher model. This slide suggests that the accuracy of the teacher and student models has strong positive correlation, which again supports the assumption that using better teacher models in KD generally results in better student models. We find that the number of data points falling into the shaded blue areas is non-negligible, which supports that even if the teacher model is worse than the baseline, it is still likely that the student model can outperform the baseline after KD. To study the impact of the ISKD parameter alpha on accuracy, we use the ResNet 18 as the network architecture of ISKD and the same random seed 1, repeat E2, E3, and E4 corresponding to the CUB 200 and Oxford 102 datasets with different alpha values, and report the student's accuracy in this slide, where with the red lines mark the baseline accuracy, which is the student's accuracy in the previous KD iteration reported in Table 1. For each subfigure, the teacher model is fixed as the corresponding one used in Table 1. The triangular points in each subfigure are the accuracy reported in Table 1 using the alpha values chosen for pothole classification, so their corresponding accuracy is not necessarily the best. This slide shows that the student model outperforms the baseline in each KD iteration of ISKD under a wide range of alpha values, which supports that ISKD is flexible in terms of parameter selection. To sum up, we propose iterative self-knowledge distillation ISKD in self-KD to improve pothole classification accuracy when training lightweight models given a fixed number of training epochs. Experimenting on 3 pothole classification datasets and 6 other datasets associated with generic classification, fine-grained classification, and medical imaging application, we show that ISKD outperforms the state-of-the-art self-KD method for most cases, given the same number of training epochs, and that ISKD has wide applicability to various tasks without the need of a given teacher model and extra trainable parameters. In addition, we show more evidence supporting that the performance of the student model can benefit from self-KD even when the pre-trained student model, which serves as the steer model, is only moderately trained. Our study on the impact of the weight balancing the objectives of ISKD shows that even if we choose different weights, deviating from the weights we initially use within a reasonable range, the student model can still improve over KD iterations, which supports that ISKD is flexible in terms of parameter selection. Please join us at the ICASSP 2022 poster session of this paper. We look forward to seeing you then. Thanks for watching this video.